All right, chapter 19. So here's a review lecture where I'm going to put it all into like hopefully what will be 10 minutes. We'll see. Okay, chapter 19, magnetic fields, breaks down into two major ideas. Major idea number one, major idea number two. And I have the equations written out right here for each major idea. Now, what is major idea number one? Major idea number one is, what do magnetic fields do? What do magnetic fields do? The answer is they exert force on moving charged particles. Okay, now this is the fundamental equation for the force of a magnetic field on a moving charged particle. Q is the charge moving in the magnetic field. V is the velocity. B is the symbol for magnetic field. And magnetic field is measured in a unit called Tesla. And theta is the angle between the velocity and the magnetic field. Theta is the angle between the velocity of the charged particle and the magnetic field. Now, what do we know about the force of the magnetic field? The force of the magnetic field is always going to be perpendicular to B and V. Okay, so let me show you what I mean. Thanks. Okay, so say that this represents the velocity of the particle, and then say that the magnetic field is crossing that velocity. The angle between the velocity and the magnetic field is this theta right there. Now the force of the magnetic field is going to be perpendicular to this plane. Remember from geometry, two lines form a plane. So B and V cross each other. The force of the magnetic field is either going to be into the page or out of the page, perpendicular to both magnetic field and velocity. You guys remember this? Where are my vectors? So look, this vector right here represents the magnetic field. This one represents the velocity of the charged particle. What I'm saying is this: the force of the magnetic field is going to be perpendicular to the plane that's made by B and V. It'll either be perpendicular this way or perpendicular that way. Now, how do you figure out which way it's going to be? Right-hand rule number one, which is called the flat hand rule. Keep your hand flat. Your four fingers are the magnetic field. Your thumb is the velocity of the charged particle. The palm of your hand is the force. If you're dealing with a positive charge. If it's a negative charge, then the force will be out of the back of your hand. Okay? So let's apply right-hand rule to this situation that I drew on the screen. All right, so you put your four fingers in the direction of the magnetic field, your thumb in the direction of the velocity. Which way will the force be? Into the page or out of the page? Out. So I'll put a dot right here. Dot represents out. The force of the magnetic field will be out of the page. Okay, right-hand rule number one. All right, now, hey, this second equation is in my notes, but I didn't talk about it in class last week. Okay, so here is how you calculate force. This second equation is used for when the moving charged particle is current in a wire. So let me give you a situation. So say that these x's here represent a magnetic field. So x's are into the page. So we have a region of magnetic field. And then what I'm going to do is I'm going to hook up a circuit. So I'll put a battery here. There's a battery. And I'm going to run this circuit through the magnetic field. Now guys, what is current in a wire? So here we have current coming out of the battery. The current goes like this and then through the magnetic field. Guys, what is current? Moving charged particles. That's all it is. So if you have current running through this wire right here and it's in a magnetic field, will that wire experience a force? It definitely will. And let me show you how to calculate it. So it's really, so this second equation, F equals BIL, it's the same thing as QVB. Let me show you why. So F equals QVB sine theta, which we already talked about, but let's figure out what V would be. So let's look at a positive charge cruising through the magnetic field, right? It's inside the wire. This positive charge is inside the wire, and let's say that the distance from here to here is L. That distance is going to be L. Well, what would the velocity of the charge be? The velocity of the charge is going to be L over T, right? All velocity is distance over time. So this is going to be F equals Q L over T times B sine theta. What's Q over T? Q over T is the definition of current. So we get this equation, BIL sine theta. The book says ILB. I don't like ILB. You want to know why? Because it doesn't spell Bill. Right? Just remember, what's force equal to? Bill. It's Bill, dude. BIL. It's the same thing as QVB, but it's for when you have current in a wire, where L is the length of the wire. Okay? All right, last thing. And believe it or not, we're like halfway done. So let me erase this. So oh, dude. Dicky-doo. Okay, let's refer to this. So the last thing I want to talk about is this equation here, R equals mv over qb. So this is the equation for when you have a charged particle traveling perpendicular to a magnetic field. So again, this represents a region. This right here is a region of magnetic field going in. And then let's send a charge into this magnetic field. So velocity to the right. So the charge comes into the magnetic field. The velocity is to the right. Which way would the force on that charged particle be? You do right-hand rule number one. The force is going to be up. So what's that going to do to the motion of the charged particle? It's going to cause the charge to curve up. So now the charge is here. The velocity would be that way. Which way is the force now? So do right-hand rule again. Force is now that way, right? So what's the charge going to do? It's going to curve that way. So now the velocity is this way. So now the force is that way, right? So now I'm going to erase all the velocity vectors. Let's just get rid of velocities and look at the force. What do you notice about the force? It points to the center of a circle, right? So the idea here is the force of the magnetic field, FB, is acting as a centripetal force. Okay? So the equation for force magnetic is QVB. QVB sine theta. Ooh, what's the theta here? 90, right? Why is that 90? Well, which way was the velocity? To the right. Which way is the magnetic field? In. What's the angle between to the right and in? 90. Sine of 90 is 1. Okay. What's the equation for force centripetal? mv squared over r. See, really all I did here is I summed the forces. You sum the forces. The only force on the charge is force magnetic. Sum of the forces equals ma. That a is a centripetal, which is v squared over r. Okay, so let's see. So one of the v's cancels, and we're left with qb equals mv over r. So you rearrange that, and you get this. Okay? So basically, long story short, when a charged particle moves perpendicular to a magnetic field, you get a circular path, and then that's the equation. Should you memorize this equation right here? Should you memorize that? I wouldn't. What should you memorize? This idea. You should be like, oh, when a charged particle moves perpendicular to a magnetic field, the force of the magnetic field is the centripetal force, and then you can derive it pretty easily. Make sense? Okay, Major idea number 2. We're almost done. Major idea number 2 is very quick. Okay, major idea number 2 is what? What is major idea number 2? Where do magnetic fields come from? Moving charged particles. And you're like, well, wait a minute. I thought magnetic fields exerted force on moving charged particles. They do, but they also come from moving charged particles. Now, where can we find moving charged particles? In a wire, which is why you don't want to buy your house underneath power lines, because you'll be living in a constant magnetic field, which is not too good for you. Okay, so current comes out like this. Right, I just drew a circuit. So let's section off an area right here. Ready? Let's look at this area. So the current is going through this wire, which is moving charged particles, and that's going to create a magnetic field. How do magnetic fields travel around a wire? In a circle. So how do we figure out which way the circle is going to be? It's one of two ways. It's going to be this way or that way, one or the other. How do we figure it out? Right-hand rule number 2, also called the curved hand rule. Right-hand rule number 1 is flat hand rule. Right-hand rule number 2 is curved hand rule. So how do you do the curved hand rule? Stick your thumb in your neighbor's ear. No, I'm just kidding. Stick your thumb in the direction of the current, and then the way that your 4 fingers curl is the magnetic field. So which way is the magnetic field up in this region up here? It's going to be going out. How do I know that it's coming out? Well, stick your thumb in the direction of the current. Your 4 fingers are coming out like that. Now, what's the magnetic field doing on the other side? Going in. Now, how do you find the magnetic field at a distance from the wire? So say that you go R, a distance R from the wire. How could you find the magnetic field like at that distance from the wire? It's this equation. Magnetic field equals mu naught I. I is the current. R is how far you are from the wire. And mu naught is a constant. So don't memorize it. I'll give it to you. It's 1.26 times 10 to the negative 6 Tesla meter over amp. And that really sums up the chapter. So let's look at a homework problem.